Today's lecture is going to cover the research design and methods, as we have been discussing. It's Module 2, Lecture 3. However, I want to take you to the WebCT, to a couple of links that I have emailed and will eventually post with the course materials for the class, and hopefully the links will last forever. So let's go to the computer and I'll show you the email that I had sent. This was in October 6, 2005, so for future reference, these two links will be posted on the course permanently, but for this particular semester, you can reach them through here. And what we're proceeding to discuss in class now is the research design and methods. Will start with the global concept of how research is performed, then talk about sources of variation, how we control them, and how we design experiments with statistics in mind, and we determine the potential impact through power analyses, as well as estimate sample sizes after having performed some pilot studies, or even from information gathered from literature research. You can make an estimate of how large of a sample size you might need to use to complete a study, and do a power analysis to make sure that you get this level of impact. And we'll have that in future lectures, not today's, but I want to give you the opportunity to visit these sites in anticipation of that. This particular site is for acastat.com, and you see obviously they sell many different types of software related to this, but they have this site that is available, and there are many things that can be completed or evaluated through here, such as the elements of the scientific model, levels of data, association, external and internal validity, all of which are in upcoming lectures. And as well, there's what we're moving toward, the measures of central tendency, of variation, standard tables, proportions, hypothesis testing, and then comparing means through a variety of approaches. And then in the appendices, there is the basic formulas, many of which we will be discussing as well. And I thought this one, I guess this one doesn't do the estimation of the sample size. But the other site, oh, here's sample size estimation. So there's an entire section on sample size estimation, the criteria for proportions, or comparing test when there's a test between two independent sample means, which is one of the more common types of studies that we perform. And then here at StatSoft, there's information on the power analysis, and I also found other sources with a Google search searching sample size estimate, and some of those were for more complex types of experimental models, such as with DNA microarray, a newer type of method, and therefore a new approach to determine the statistical power of those. So these are good sources of insight, in addition to what little or none might be in our textbooks. So let's jump over then to the Module 2, Lecture 3. I want to complete this, and then as I'm in here in the classroom, I'll end this and notify the people doing the recording in the back that we're going to stop at this one, and then I'll go on and complete the Module 2, Lecture 4 subsequently. So we are continuing with our discussion of the research design and data management, and we're beginning to think about the principles of statistical design, because this is the starting point. It is the strict starting point for all types of experimentation And it's critical that this is kept in mind. We don't always start with this in practice, as most of us know. We quite often find ourselves at the bench collecting data, completing subsets of experiments on experimental groups, and then begin to ask ourselves how we're going to work with the data that we're collecting. But in reality and over the long run throughout a profession, you transition over to starting from statistics first. So these are the sources. Principles of Experimental Design for Life Sciences, one of the course textbooks. Statistics and Experimental Design, an introduction for biologists and biochemists. Understanding Medical Research. This is one of the ones that I find to be especially useful in helping to achieve that, not only medical research, but research in general with the way that this small textbook is set up. And then our Practical Research Planning and Design textbook that we're using for the course as well. So we start first, of course, with the one-to-one-to-one correspondence between the study objectives, and our prior lectures have been discussing the study objectives, identifying the problem, setting up the hypothesis, identifying subproblems, goals, objectives, and aims, and the general outline for a research proposal and how to go about it. So we should have a level of confidence of how to approach this aspect of setting up the study objectives. 3 objectives for a 3 to 5 year research period is recommended, or any one grant proposal in that sense. It's directly related to or corresponds with the the experimental design and the statistical analysis. And as I mentioned today, you really need to work on study objectives and hammer out a preliminary experimental design, go to the statistical analyses and come backward and make sure that the design you put together coming from the literature and your ideas really is appropriate for the type of statistical analysis. Or if your experimental design from the perspective of developing your study objectives becomes so complex when you try to apply a statistical test to it, then you may go back and rethink your approach and set up your experiments slightly differently so that the complexity of the statistical analysis is simplified. I'm not saying that you play with it so that you're definitely going to get something that's statistically significantly different, but there's ways of reducing the complexity of experimental design so that you answer questions one at a time. You still might have quite complex statistical analyses, but it might not be one where you've got to put in 50,000 different variables, and the output that you get from the test, if there is one for it, is so complex you may never be able to understand it or explain it. So this is really what's being reflected here. An appropriate statistical test will let you have true confidence in your experimental design, its limitations, and its simplicity as much as possible, and let you apply your outcomes to the study objectives. In other words, test your hypothesis directly and either support it or not support it without major complications or diversions. So we start first then thinking about variation. The worst enemy in research, as we all know, is variation, and we're going to identify some of the sources of variation. Of course, the first one that we recognize is natural variation. So we have to control for variation before we can think that we have any type of reasonable experimental design. So we know that biologists studied nature. We're natural scientists from the very beginning, I guess, historically, and it was simply discovered that there is differences among individual observations, even if it's on the same individual, whether it's a chemical or an animal. So this is just part of nature. So even if you have the most highly controlled work, you're going to have variation from one measurement to the next. And so there are tests and procedures to handle all of that and build the confidence that you are that the variation in your sample is either due to a real difference between your experimental groups or is limited only to the natural variation to the highest degree of control. So the common factor is that experimental units, plants or animals, vary among themselves, obviously naturally, even when they are treated as exactly alike as possible. And of course it does differ on different levels. If you're doing animal behavioral studies in the wild versus animal behavioral studies in a very controlled environment in a laboratory, you're still going to have more variation within each sample group than if you were studying the behavior of maybe one chemical in the brain associated with an instantaneous behavioral response, such as to stress or a chemical toxin or something like that. So the natural variation does have ranges depending upon the level of observation. So it's called experimental error, although that doesn't really sound so nice, but it's the real term for it. Random variation or residual variation are the terms that we'd prefer to hear applied to this type of variation. So we turn then to statistics, and it is mathematics as we know, and we'll look at many of the formula used for statistical analyses so we can begin to reinforce, hopefully we remember some of our statistics, but reinforce the value of each different type of test and what kind of information the outcome or the results of the mathematical problems solving contribute to our understanding of the studies and, of course, the conclusions, limitations to the conclusions that can be drawn. So we know about populations versus samples. So populations really are the collective set of individuals. So it's the items or units or individuals all having the same characteristic, existing in the same controlled conditions or environment, and as large as your brain can let you imagine. But it doesn't always have to be as large as you let your brain imagine. A way to study populations is to approach it from the perspective of what's reported in the literature. You may take a sample, say you're doing a pilot study, you may take some samples and generate a mean or some value from that, and you ask yourself, is this equivalent to the general population? So you go look in the literature and you see what everybody else has been able to measure, and if your, say it's the mean for your sample group, is extremely close to what everybody else has been reported or within normal range, you feel confident that your sample is representative. If and blood pressure is one that comes to mind because I've done some work with blood pressure. So if you're, we go to humans, we're all familiar with that. we know that 120/80 is the normal population blood pressure, because it's been studied so much and on so many people that it's highly established. So if you're going to study a new human population and you pick 5 people at random, measure their blood pressure, and you have 150/100, you don't think that you have a new normal level of blood pressure. You suspect that you've got a population of individuals, very likely all of whom are suffering from high blood pressure. So that's the way that can work. It's not an unachievable number to be able to evaluate. There are ways of going about it. So if you are taking a sample for a pilot study and you get some values, you have to make sure that it fits into the theoretical framework. If everybody else examining this is getting levels in a certain range and yours is nowhere near it, you probably have invalid data. From the perspective of anybody that might be reviewing your results, they're going to consider your data invalid because it doesn't represent the normal population values. So the sample, we know, is a subset of a population, and it's got to give a good representation of the population. if the statements inferences that we make are to be of any use. As I said, if it doesn't fit into the theoretical framework, everybody's going to disregard it and discount it. So that's a random sampling from a whole population. And how this works for bacteria that you've grown in the laboratory or rats that you've ordered from a distributor. It's kind of hard to visualize that coming from an entire population, but we know indeed that is the accepted approach. So from statistics then, we understand that there are two approaches. There's a parametric statistics for normal distributions of data. We all know that Gaussian curve, and that's what we're going to be thinking about, the frequency distribution of our data points over the range of data in the data set. So this is where we're going to start thinking about that bell-shaped curve. If it is a true bell-shaped curve, if the population data points, the frequency of the population data points fit that, near perfectly, then you have a normal distribution. If not, then you don't have a normal distribution. Then you have to use non-parametric statistical techniques. So we're going to introduce ourselves to both parametric and non-parametric types of approaches. For the parametric, the descriptive statistics is probably what most of us are familiar with, and that's involving the measures of central tendency, variation, and correlation. And these are what we're going to begin focusing on first to remind ourselves what these are. And then there's inferential statistics involving predictions or estimations or hypothesis testing. And this is what we are less commonly encountering in biological research. But we still will talk about it so that we can understand how this approach is achieved, so that we have a better appreciation for the methods that we do use most commonly. So first then, let's think about describing population characteristics. We're going to talk about values for population and values for our sample. So we need to think about how we collect these values and what types or categories there can be, and therefore what types of approaches are used to evaluate our data points, our samples. So the types of data can either be quantitative or qualitative. Continuous data, quantitative data, is what most of us probably deal with. It's measured on a numeric scale that represents a true quantity, blood pressure in millimeters of mercury, weight in kilograms, amplitude in milliamps. So it's one which can take any value, whatever, to any number of decimal places. So there's really shouldn't be any limit to what the value could be. Now we know that you're not going to have a blood pressure of 5,000 because you're going to die somewhere by the time it reaches 250 or 300 systolic. But theoretically, if the system could tolerate it, it could be any value whatsoever. So this makes it continuous, even though biologically there might be limits. The discrete data or categorical data for characteristics. So there's no question of decimals or fractions, and you can write down a list of possible values which the recorded number may take. Present, absent, +1, -1, 0, and 1, whatever it might be. Male, female, blue, brown, hazel. Numbers of female rats in litters containing 5 rats altogether. So these are types of discrete or categorical data. And of course, we can leak it out now. You very likely would not be doing, and most of the time definitely would not be performing parametric analysis on these types of data points. The ordinal is another type, measured in categories that have a natural order, like symptom severity, mild, moderate, and severe. So there is a ranking in the significance of the terms. The job satisfaction, high, medium, or low. So these aren't obviously numbers that you're extracting from each individual observation, but the numbers of observations in each category will be evaluated. So this makes it not a discrete measurement, it is an ordinal measurement. The values of the sample characteristics. are considered estimates of the values in the larger population. We always have to have that in mind. You can't work within a vacuum just assuming that the values you're getting from your samples, your sample observations are real unless you have a population to compare them to. If you're the first ever to make such a measurement, then you have to be sure that all the other types, sources of variation that we talk about probably and more are strictly regulated and controlled in your experiments so that you're using the appropriate standardized approach to establish population values, even if your first efforts will only provide a sample. Over time, as more and more samples are collected and more people begin making that measurement, you generate the representative population values. The categorical or discrete, you use a proportion expressed as a decimal or percent, or the rate if it's a frequency, and the ordinal, you use median or mode values to report them. So, without doubt, I appreciate that everyone knows where we're headed and remembers a lot of what we're going to be talking about, but it never hurts to see it once again. So, what we're really concerned about with looking at populations and data from samples is some estimate of central tendency, so we can end up with a single number to compare between the groups, but based upon the dispersion of the data around that point of central tendency. So important information about a data set is the range, so in this case, of course, from 69 to 92. And in this case, we can calculate the average or the mean, as we know. It is the precise center of the amalgamated values. There's also a median, the precise center of the numerical array, and there's the mode, the value that appears most frequently in the array. So sometimes these values may be the same number or very similar numbers, off by just a few decimal points, and other times they can be very different. So we need to understand that. As well, different measures of central tendency will apply to normal distributions of data, excuse me, versus for parametric versus non-parametric evaluations. So around this central tendency, we have different measures of dispersion that we'll discuss in a pretty good level of detail in future lectures. The one we all are familiar with is the standard deviation around the mean. So the standard deviation of this data set is 6.9. So plus or minus 6.9 is one standard deviation from the mean. So where we're headed is to ask ourselves, what percentage of our data points fall within one or plus or minus one standard deviation of the mean? There's also an average deviation that we don't typically encounter. In this case, it turns out to be 6. But they're both giving a feel for the dispersion of the data points around the central tendency. So as we're thinking of population and sample, we need to remind ourselves of the conventional statistical notations for various parameters. So of course, the mean for the sample population is typically x or x bar. That's the one we most often see. The geometric or harmonic mean is one that we're less familiar with. For the population, the value is mu. The sigma is the standard deviation. The lowercase s is standard deviation for population and sample. Uppercase p for the proportion or probability for population. Lowercase p for the probability or proportion for the sample. Uncertainty n or number total. We don't usually deal with an uncertainty n, but the number or total, the n value is lowercase for the sample, uppercase for a true population. So we need to keep these in mind. We are going to talk about mu's and sigmas and x bars and lowercase s's as we proceed. Obviously, we're going to talk about the lowercase n, the sample size, or the number of total observations in samples and relate it back in formulas to looking at how we calculate a value in the population versus the sample. This slide is taking us through the different scales that we just discussed, the non-interval scales and the interval scales. So the non-interval scales are the nominal scale and the ordinal scale, and the interval scales are the interval scale itself and a ratio scale. And we'll describe each of the characteristics of the scale and the statistical possibilities of each of these. So the nominal scale measures in terms of names or designators of discrete units or categories, as we had mentioned. So nominal obviously means name. So there's some descriptive name for the measure. So it can be used to determine the mode, the percentage values, or a chi-square, predicting the frequency of occurrence of certain things. An ordinal scale measures in terms of such values as more or less, larger or smaller, but without specifying the size of the interval between more or less. So it can be used for determining the mode, percentage, chi-square, median, percentile rank, or rank correlation. So in other words, the type of data you collect limits the type of statistical approaches you would use to evaluate it. The interval scale measures in terms of equal intervals or degrees of difference, but whose 0 point or point of beginning is arbitrarily established. So you can determine the mode, the mean, the standard deviation, t-test, f-test, and the product moment correlation. So this is sounding more like types of measures that we might make. Ratio scales measures in equal intervals and an absolute 0 point of origin. So you can determine the geometric mean, harmonic mean, percentage variation, and all the other statistical determinations. So most often we find ourselves in a setting where we're collecting data in a standard format, within a laboratory routine, and a standard approach is used. I challenge you to learn the material that study the material carefully that we're presenting, and be able to justify the statistical procedure that you do use, and if there is an inconsistency, take it up obviously with the PI in the lab to make sure that you understand why things are being done the way that they are done. So the simple tests for the kinds of data measurement, one object's different from another, so you have a nominal scale. One object is bigger or better or more of anything than another. You've got an ordinal scale. One subject is so many units, degrees, inches more than another. You've got an interval scale. One object is so many times bigger, so many times as big or bright or tall or heavy as another, and then you have a ratio scale. So there's ways of asking questions to help you understand what type of scale you have. So again, the nominal, ordinal, interval, and ratio scale, we can determine the matching measures of central tendency to the categories of these particular types of data. So for a nominal scale, the mode is used. So it's the numeral representing the category with the highest frequency of occurrence, and it's prediction. It is the prediction most likely to be right for that particular set of data points. For the ordinal scale, the mode, as we had described above, so it is appropriate for discrete data only. The median is another central tendency, so it's the point above and below which lie 50% of the cases, so it sits right dead center, and it is one of the observations. So it's the prediction that is just likely to be too high as too low. It is more stable than the mode because it is truly a central tendency, of course. For the interval, the mode, the median, as for describing the ordinal scale, And the mean, of course, is x bar equals the sum of x over n. They're using the uppercase n there, and they shouldn't be. Well, I guess they're talking about the, no, it just doesn't fit, does it? It should be the lowercase n if they're using the x bar for the mean. But anyway, the prediction that makes the sum of the errors 0 and makes the sum of the squares of the errors a minimum, and it is more stable than the median. And of course, you use it whenever it is appropriate because it is the more stable, actually the most stable of the central tendencies. And then the ratio, mode, median, mean, and then the geometric and harmonic means for special situations that, as I said, we don't often encounter. Continuing with the matching the measures of dispersion to the category of the data. So for nominal data, except for verbal descriptions longer than, it's inappropriate for indicating measures of dispersion. So you just won't have any value that would represent dispersion around the mode. I think that was mode, wasn't it? Yeah. For ordinal, you use the range, the maximum minus the minimum plus 1. That's not really stable. Interquartile range, center quartile range, or other interpercentile ranges. So some feeling of or representation of the percentage of data points that fall within a certain distance around the central tendency. And we'll look at different styles of graphing data for each of these as well. And remind ourselves that we don't always see all these types of graphs, and we have to wonder if people are presenting data appropriately at all times. The range quartile ranges, as for the ordinal scale, work for intervals sometimes. The average deviation, most often, as I said, we use the standard deviation, and here we see the formula. We'll talk about it again later, but standard deviation and variance, of course, it's the square root of the sum of x squared over n, and the variance is, of course, just the s squared. So you take away the square root, of course, the sum of x squared over the sample size. Then the ratio is various ranges, the average deviation, variance, standard deviation, variance, or coefficient of variance. So important to understand the type of data you're collecting and the approach to evaluating measures of central tendency as well as dispersion around that central tendency. Then, of course, we have to think about the presentations of the population data. So there's frequency curves for the continuous variates. So how frequently do data points occur in your data set? And of course, the normal distribution is that model for continuous data, and it's pretty much the only one that we're going to be dealing with for our explanations in the class. We're not going to be talking about any data sets that are skewed to the left or skewed to the right. We'll just think of the normal distribution. Therefore, depending upon the type of data that you have, you actually display it differently graphically. There's some overlap, but some are very specific. So the ordinal data, the discrete data, would be in bar graphs. So the order and the heights of the bars do have mathematical significance. The continuous data would be histograms. So the order and the heights of the bars have the mathematical significance, and adjacent bars must be contiguous. So a histogram is different from a bar graph. In a bar graph, the bars are separated. In a histogram, they must be contiguous. They must contact each other. The frequency polygons and cumulative frequency and cumulative percentage graphs are rare in our fields of study, so I won't comment on them. The interval for discrete data, again, the bar graphs, the heights, order, and the widths, and the spacing of the bars have the mathematical significance, and the area inside the bars is proportional to the number of cases. So it's very specific in that sense. For continuous data that we are most accustomed to, the histograms, it says for the bar graphs, the adjacent bars must be contiguous. Frequency polygons, horizontal spacing of the points has mathematical significance, and the area under the curve is proportional to the number of the cases. Cumulative frequency and cumulative percentage, and the shape and the distribution is meaningful. In other words, the skewness and kurtosis can be described, and the theoretical distributions, for example, the normal that we'll consider, can be approximated by the obtained data. And then the ratio, bar graphs, histograms, frequency polygons, and so on and so forth. So different data is graphed differently, and it's important to understand and appreciate that. In many cases, as I said, we do things routinely because that's the way we're trained to do it. We should understand why we do it a certain way, and we are very often expected to be teachers and trainers of new people in the laboratory, and so we should always explain why we graph something a certain way and why it is important and how we determine it. We, in much of our work, probably don't generate a distribution of scores in a normal curve, but quite often we'll run statistical tests where there will be a test for the normality of the data, and if you pass that test, then you go on to use parametric statistical evaluations. So we do work with this. We should be able to recognize it and understand it. So with the normal distribution, the mean is the center point, as we know, and standard deviation is the measure of dispersion. So plus or minus 1 standard deviation from the mean should be the inclusion of 68% of your sample set. Plus or minus 2 standard deviations should be 95% of your sample. Plus or minus 3 should be about 97%, and plus or minus 4 should be roughly 99% of your data points included. This is the real Gaussian curve, the normal distribution of data. Our data will not always look exactly like this, and that's what we want to begin to appreciate, because what we will begin talking about in future lectures is seeing something like this and immediately turning it into a bar graph, where there's a bar that represents the mean for the sample, and then a standard and some type of error bar, standard deviation. Standard error of the mean is what we see most commonly to represent the dispersion. And so we're going to go back and forth between the shape of a curve like this and our imagination of how a bar graph would look representing that. So here are 2 examples of data points. The one above, the data tend to be closely clustered around the mean. So we have a central tendency, and the dispersion is tight. So it's the typical, the representative, the most common data, the type you would like to have. This is another data set where the dispersion obviously is much greater. So as the data are dispersed farther and farther from the mean, they tend less and less to resemble the data qualities of the mean, and the remote data is less typical and less representative. So the more your data is dispersed away from the mean, then the less it is to fit that pattern that we saw before, where 99% of your data points are within the 4 standard deviations. But also, we immediately envision that the standard deviation for this is going to be greater than the standard deviation for this. So we immediately can envision in our mind those 2 curves, the one that is tight like this. Okay, that's not a very good curve. The one that is tight like this, and the one that is broad like this. So what we can almost automatically begin to see is that we would have a bar graph, even if the mean values were different on the actual scale, on the numerical scale down here, if this mean was 100 and this mean was say 90, we're going to have a standard error bar on this one that is much taller than the standard error bar on this one. And the problem is the downward swing of this one overlaps the upward swing of this one, and these would not be statistically significantly different from each other. So if we put these two on the same scale, with 90 here and 100 here, and we're going to have a nice tight curve here. I didn't get it just exact. And then our other one is going to overlap like this. So we see that we have a significant overlap of data points between the two samples. So your statistical test is not going to be able to tell you that these, even though it's a difference of 10, whatever the units are, your statistical test is not going to be able to tell you that these two samples are indeed different from each other. There's too much overlap in those, and we can assume the same thing with these. The height is quite a bit bigger, but the error bars overlap, so it is unlikely to be significantly different. So this is the skill that we're trying to develop as we continue with our presentations. So this completes the discussion on Module 2, Lecture 3, and we'll change over to Module 2, Lecture 3, and we're going to switch over to Module 2, Lecture 4.